those 2D CFTs from 4D n equals to 2 gauge theory.
Thank you very much. It's a great pleasure and honor to be here, so I'd like to first start by thanking the organizers for inviting me. And today I will talk about my work with Fernando Alday and Davide Gaiotto. Both are in the audience today. The message today is very, very extremely simple. So the idea is, well, very nicely summarized by Davide in the last talk. But the idea is just to start wrapping n M5 branes on a 4-manifold times Riemann surface, well, 2-manifold. Then, well, by somehow Kahl-Klein reducing in two ways, you can relate a physical quantity on the 4-dimensional side and another physical quantity on the 2-dimensional side. So that's the message you have to remember. So that's the only thing. So let me get into the details from now. OK. It's going OK. So first, let me remind you how what kind of 4D theory you get by wrapping n M5 branes on a Riemann surface. The good thing is that Davide Gaiotto came up with a nice, very, very nice rule to read off 4-dimensional Lagrangian, just given the ingredients of the Riemann surface and combining them. So suppose you want to make a 4-dimensional n equals 2 gauge theory with SUN gauge group with 2n hypermultiplets in the fundamental representation so that the theory becomes superconformal. The only thing you have to do is to choose the ingredients. So if you wrap n M5 branes on a 3-punctured sphere with a particular choice of punctures, you can get n fundamental hypers. I mean, n by n, 3 hypermultiplets. But if you want to couple that to one SUN gauge group, you get n hypermultiplets transforming in the fundamental representation. So you take one of them, and because you want 2n of them, you take another 3-punctured sphere. And the last rule is that if you have a tube of n M5 branes, you get SUN vector multiplet. So in order to get SUN gauge group with 2n fundamentals, you combine the 3 ingredients into a single Riemann surface by connecting one of the punctures out of 3 for the 2 3-punctured spheres by this tube, and you get this nice 4-punctured sphere. And because the length of the tube is basically inversely proportional to the gauge coupling, the cross ratio of the configuration of 4 points on the sphere becomes basically the gauge coupling, UV gauge coupling of this superconformal theory. So that's one thing. So let me explain a bit more carefully how you get 4-dimensional gauge theory, out of wrapping 6-dimensional theory on a Riemann surface. So the idea is that you start from an M-theory configuration, which is of the form 4-dimensional flat space, a cotangent bundle on a Riemann surface, which is 4-dimensional. Therefore, it is hyperkähler, at least close to the 0 section. And you have, well, 3 more directions because it's 11-dimensional. So 4 plus 4 plus 3 is 11. Now, you wrap n M5 branes on this Riemann surface C with a number of punctures. So the locus sigma on which 5 branes wrap should be some nth degree n polynomial, so that for each point z on the Riemann surface, you should have n solutions to this equation so that it describes n points on the direction tangent to this Riemann surface, right? So for a given z, you have one equation. You solve that. You get n sheets covering this Riemann surface C. So you can think of these coefficients appearing in the defining equation of the Riemann surface as the world volume fields of 6-dimensional theory, which is the low energy limit of n coincident M5 branes. So in order to preserve supersymmetry, or just by the fact that it's embedded in this cotangent space, you see that this phi of phi k is a degree k multi-differential on the Riemann surface. So you can think of it as having spin k on the Riemann surface. So by solving this, you get the one form because you're living in a cotangent space of C. And this one form, which is the position along the cotangent direction, is exactly the Seiberg-Witten differential. So this is the very nice way to determine the Seiberg-Witten differential out of this construction. So from now, you will see two Riemann surfaces appearing everywhere. So you need to distinguish them. One is Riemann surface C, which is the base on which you wrap the NM fibrils. And the other is sigma, which is the N-sheeted cover. So the sigma is the class traditional Seiberg-Witten curve. And I'd like to call this base the Kyoto curve. Right? So you need to differentiate the two. Now, this construction, in fact, has been known for a long, long time. For example, if you want not SUN with two N flavors, which is super conformal, but something asymptotically free, like pure N equals 2 gauge theory with SUN gauge group, the Seiberg-Witten curve was determined by various people, but the form which suits our purpose today is the one found by Martinek and Warner, which has this form. And in fact, this is exactly the form we need to get by wrapping M fibrils. So you can think of this coordinate z as the coordinate of the sphere. And because you have z and 1 over z, you have two punctures, one at z equals 0, the other at z equals infinity. So in order to convert this equation to the other form I showed you in the previous slides, all you have to do is to move this term on this side and multiply by a suitable power of dz. What you get is that phi 2 of z up to phi n minus 1 is just given by this coefficient uk times this standard differential. But phi n behaves slightly differently because of this z plus 1 over z. So the thing you need to remember is that phi k for phi 2 to phi n minus 1 behaves like just 1 over z to the kth. But the last one behaves slightly badly. That's the important thing which produces asymptotically free theory. OK. So thanks to this construction by Davide, we now have a map or a functor or whatever. I don't know what is the precise mathematical name for this, because it's a very strange thing, which assigns for a given Riemann surface with a set of punctures a four-dimensional field theory, right? So it's a strange map which maps a given two-dimensional object into a 4D gauge theory. And the nice thing about this map, so I call this Gn in the case if you wrap n M fibrils. This map Gn behaves very nicely under degenerations of C. So degeneration means that you split the Riemann surfaces into two. So if you split C, as I just told you, you have a very long, thin tube connecting two parts of the Riemann surface, which means that you get a very weakly coupled SUN gauge group. Because as I said, the gauge coupling constant is inversely proportional to the length of the tube. So this means that if you split a Riemann surface into two, and under this map, the 4D gauge theory you get also gets split into two disconnected 4D theory. Now, suppose we are given another quantity of some physical quantity which is defined for any 4D field theory so that you can calculate a number. Then you combine these two maps. And suppose this z is some multiplicative quantity if you're given a totally separated theory. Then you can easily see, because this map Gn factorizes nicely under the degeneration, this map, which just assigns a number for a given Riemann surface, also factorizes under the degeneration of the Riemann surface. So morally speaking, this means that this combined map is a 2D CFT, because 2D CFT is, abstractly speaking, a set of assignment of numbers for punctured Riemann surface, which behaves nicely under the decomposition of the Riemann surface. Okay, so this is a rather mathematical way to present how to understand what is going on. But the slightly more physical way of presenting things is to start from the 6th dimension again. So we are wrapping n and 5 rings on the 4-manifold times Riemann surface. And let's calculate some quantity z of the 6th-dimensional theory. And in order to reduce the calculation down to 4D or 2D, you need to assume that this quantity z is somehow protected by, well, supersymmetry or anomaly or whatever, topological reason or whatever. It doesn't matter. So suppose it can be evaluated by Kaluza-Klein reduction. So then if you think C2 to be very, very small, you can perform the Kaluza-Klein reduction to get some 4D theory on X4, and you need to calculate something here. On the other hand, if you think X4 to be very, very small, you reduce along this direction, and you get 2D theory. But as David emphasized, we don't know much about 6-dimensional theory, so you cannot really perform this reduction at our level of understanding here. So what we can do is to take inspiration from this structure and forget about this part and try to match something calculated on this 4D theory and another thing calculated on the 2D side. Okay, so what exactly do we get by choosing various z? So what we found is that if you take Nekrasov's instanton partition function as the 4D quantity you calculate, that will translate to some conformal blocks of Virasoro algebra or Wn algebra. If you take instead full partition function of the gauge theory on round S4, then we found that it becomes the correlation function of Liouville theory or Toda theory at b equals 1. You can also consider calculating anomaly polynomials of 4D theory and 2D theory and compare them, and they nicely agree. And also, a group from Stony Brook studied the superconformal index of the 4D theory, and they got the topological quantum field theory on the Riemann surface. So these are the list of the things studied so far. But of course, you can take whatever physical quantity you like in the 4-dimensional side and get another nice mapping using this general construction. So using the rest of my time, I would like to talk about this first thing. And I think because Nekrasov's instanton partition function is not that well-known subject, I would like to spend a bit of time reviewing how the calculation of that thing is performed. Okay. So Nekrasov's instanton partition function is a very nice object which contains in the small epsilon1, epsilon2 limit the standard prepotential, which determines the Lagrangian low energy properties of this theory. So the definition goes like this. You take a 5D version of the same theory, well, which you can do because it has n equals 2 supersymmetry. So you just take the same matter contents and consider a 5-dimensional version of the theory. And because we want to consider a 4D theory in the end, you compactify that on a circle with length beta, but you glue two ends of this segment beta by a 4-dimensional rotation omega, and also the gauge rotation g. And as you know, 4-dimensional rotation can be decomposed into rotations of two planes in it. So it can be parameterized by epsilon1, which is the angular velocity along this 1-2 plane, and epsilon2, which is the angular velocity of the 2-3-4 plane, right? And gauge rotation is given like this. And you need to take a nice 4-dimensional limit. So it's a strange configuration, but the idea is that because of this rotation, it gives something like harmonic potential around the origin of the coordinate. So it effectively confines any excitation around the origin of the spacetime. That's why you can talk about the partition function, because if the spacetime is infinite, I mean, partition function is either infinite or 0, right? So it doesn't make much sense. So this is it. So this is the definition of the instanton partition function Z, but how do you compute that kind of strange thing? Well, unfortunately, I don't have that much time to review. Oh, it doesn't work anymore. Review how it goes. So it is a BPS quantity which gets its contribution only from BPS sectors. And the BPS sectors in gauge theories are basically instanton configurations. So let's say M moduli nk is the k instanton moduli of UN gauge theory. Then this partition function is a generating function or the summation over all of the instanton sectors of something very complicated, which I don't want to talk about. But there is a very effective way to calculate it using this action of SO for rotation of the space and the SUN action, which is the global gauge rotation at infinity. So there is a nice mathematical theorem which says that in such a situation, an integral over the whole moduli space becomes just the summation over a contribution from the fixed points under this group action on the instanton moduli. And fortunately, mathematicians have classified what kind of fixed points there are inside this complicated space, k instanton moduli of UN gauge theory. So in the string theory language, you have n d3 branes, and instantons can be thought of as d instantons. So they just stack naturally into close to the origin, forming the Young diagram. So what you have is a summation over the Young diagram, and each Young diagram gives some particular contribution. So it's a very simple thing, which you can explicitly evaluate. In the case of pure SU2, what you have is a summation over the Young tableau, but just the contribution from the gauge field. So this G stands for gauge. So this is a very complicated thing, but you can see this in this way. Let's introduce a vector space, which is an assignment of a complex number to each of the fixed points. In this case, each fixed point is labeled by two Young diagrams. So there's number V empty, empty, V empty, one box, V one box empty, blah, 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 right? And let's introduce an inner product in this space using this formula. So you just take the product, but divide by this. So this object can be easily realized as an inner product of itself of this stupid kind of vector. So for a Young diagram with total number of k box, you associate lambda to 2k. Then this inner product of itself is the SU2 instanton partition function. In the case with SU2 with fundamental matters, for example, if you have 4 flavors, it's better to think of having 3 SU2 gauge groups, but putting 2 gauge groups to be in the 0 instant sector, effectively making it a flavor symmetry. So in that case, you not only have gauge field contributions, but you also have hypermultiplet contribution. Hypermultiplet contribution, of course, depends on the parameter of this SU2 and the parameter of the other SU2. So you can think of this hypermultiplet contribution from a map defined from a map on the linear space defined on this gauge group to the other gauge group by this formula. So you just think of this thing as a multiplication operator, this thing as the other multiplication operator. And you can think of this Q to the instanton number as some operator counting the number of boxes. So you can represent this instanton partition function in this form. You start from a vector, apply this map, evolve some time, and apply this map again, and close it. So I just reviewed how to calculate the partition function Z for these 2 cases of pure SU2 and SU2 with 4 flavors. Let's compare this structure with the Kyoto curve, which looks very similar. For example, if you consider Virasoro conformal block associated to this Riemann surface, you would get exactly this. Because if you have 2 points, you would have just one state here, the other state here. You get the inner product. If you have 4 points on the sphere, you have one state, insertion of a vertex operator, another insertion of vertex operator, and you close the inner product. So you suspect that they might be equal, and indeed they are. So the idea is this. The Seiberg-Witten curve for two M fibrils is this. It's very simple. Seiberg-Witten differential squared is given by a spin 2 object. CFT also has spin 2 chiral object, which is the energy momentum tensor. So our proposal was to map the limit of the expectation value of the energy momentum tensor of the CFT to be this world volume field when you take this rotation parameter very small. And the central charge of the CFT is given by this formula. So this is determined by the rotation parameter. So you might say, then, how do you determine the operator V's? It's very simple using the idea. Because you know the explicit form of the Seiberg-Witten curve, and phi 2 behaves like m squared dz squared over z squared. So this translates to the behavior of the energy momentum tensor close to this operator insertion. This means that Vz is a primary of a Virasoro algebra with dimension given by this. So you plug this in, and you see the agreement of the conformal block with the necklace of partition function. In the pure gauge theory, it's also kind of similar. But you need to determine this vector W. So this is done by Davide. So as I reminded you at the beginning of the talk, in the case of pure SU2, this phi 2 not only have this 1 over z squared term, but also 1 over z cubed term. This means that you not only have this term, but also the other term. This means that the state corresponding to this insertion is not really a primary state. L2 and L3 and up annihilate this state, but L1 doesn't quite annihilate it. It has this lambda squared. So it's like a coherent state of the Virasoro algebra, which you can determine recursively. And if you take the inner product of that with itself, you really recover SU2 partition function. So the relation is this. For a given gauge theory, you can associate the necklace of partition function, and it looks suspiciously similar to the structure of the Kyoto curve. And if you calculate conformal block associated to that, you really get equality. So that's what we found accidentally. So far I just talked about the conformal blocks. So let me talk a bit about the review theory relation. So, well, we got the symmetry structure, which is the Virasoro algebra, but what we really get as a CFT. If you start from two M fibrils, there's a rough argument which tells you what you should get. So because for each tube, you need to insert one primary, insert the complete set, which is parameterized by the primary state. Primary state should be labeled by the gauge theory variable A, which is the vacuum expectation value of the diagonal of the gauge scalar in the gauge multiplet. But of course, there's a Weyl symmetry relating A and minus A. So the CFT you should get should be such that its primary field is parameterized by one variable under this identification, A, which goes to minus A. And there are a nice series of works by Teschner and Pachman, which says that just by studying the crossing symmetry, the consistency of the crossing symmetry, such 2D CFT is almost forced to be review theory. And indeed, if you use the localization calculation of Peston, we can really check that we get Liouville theory if we compactify the 4D theory further on round S4. So Liouville theory is a very well-studied subject. It describes a boson reflecting off an exponential wall. And the strength of the exponential is related to the central charge of the CFT in this way. So looking at this structure and comparing what we found, it's very natural to match the parameter b squared in the Liouville theory side with the ratio of the rotation parameter, epsilon 1 and epsilon 2. And you can really easily check using the property of special functions that something called Dorn-Otto-Zamolodchikov 3-point functions of the Liouville theory is equal to the one-loop factors appearing in the Nekrasov partition function, which enters in the calculation of the partition function on S4. And the important thing is that the Weil reflection in the gauge theory side corresponds to this reflection of the Liouville wall. Given this, it's very easy to generalize the analysis from 2 M fibrans to general N M fibrans. So there is a natural generalization of Liouville theory, which is called Toda theory. And this describes a wave propagating in n-1 dimensional space, which is reflected off by a number of exponential walls. And the exponential walls are situated such that to mimic the structure of the Weil chamber of SUN, Cartan algebra. So you can think of the wave as superimposed with its Weil reflections. And this Toda theory becomes a CFT if you choose the background charge carefully. But the interesting thing is that this does not just have the Virasoro algebra, which has T of Z, which is a spin 2 object. This Toda theory is a much more intricate object, which has not only TZ, but also W3, W4, ... to Wn, which are higher spin holomorphic objects on the world sheet. So the idea is simple. The Seiberg-Witten curve, as I told you in the first slide, is given by this nth order polynomial. And there are world volume fields phi 2 to phi n, which determines the Seiberg-Witten curve given the Kyoto curve. Each phi k behaved like dimension spin k object. On the other hand, in the Toda theory side, you have W generators, which starts from T of Z, which is the energy momentum tensor, and goes up to Wn, which is the top object. So the idea is exactly the same. We propose, this is done by Willard, but the proposal is that the expectation value of spin k object in the CFT side becomes the world volume field of this M fibrin construction in this small epsilon limit. And you identify the gauge theory web for each tube. Now we are considering basically SUN gauge group, right? So you have n-1 dimensional vector, which you identify with the momentum in the Toda theory side. And the mapping between the exponential strength and the rotation parameters are the same. So the important thing is that the Weil reflection in the gauge theory side is mapped to the Toda reflection on the Toda theory side. Okay. So what's the status of this proposal? Maybe I'm speaking too fast. So there have been many checks of this relation of Virasoro conformal blocks and the Nekrasov partition function in the case of SU2, and people study them very in a detailed way. But one of the most important things done last year is this work by Fateev and Litovinov, which appeared in December, who proved the equality of the Nekrasov partition function of SU2 with adjoint matter field with the torus one-point conformal block in the Virasoro side. So the way they did it is by showing that both sides satisfy exactly the same recursive nonlinear identities. So because they are recursive nonlinear identities, by just giving the leading term, all of the higher order terms are determined by just the recursion relation. So on the CFT side, that nonlinear recursion relation was conjectured by Pogosyan and later proved by 3 guys from Poland. And Fateh and Litvinov showed that the same nonlinear identity holds in the necklace of partition function side. So that's one proof, but the general proof has not been given. In the case of SUN with n larger than 2, things become much more complicated because we need Wn algebra. But there are nice sets of papers which really checks various calculations to high order. And it seems everything is working all right. OK, so far I talked about the case of n2 or greater than 2. Then how about U1 case? In fact, mathematicians called Carlson and Konkoff had done that in 2008. It's even before our paper. So what they did is that they calculated the necklace of function of U1 Kriba. So you just have U1 gauge group with hypermultiplets. And they showed that it equals correlator of a free boson. So it's an analog of the phenomena we observed in the simpler case, but it's proved there. So in that terminology, so I introduced this vector space which assigns complex number to each of the fixed points. This is a very standard object, in fact, in mathematics, which is called the equivariant cohomology of the instanton moduli space. So our observation just means, in the mathematical jargon, is that for the instanton moduli for n, general n, we should have naturally the structure of the Verma module of Wn algebra. And you can think of free boson as W1 algebra, so that reduces to this in their case. And the hypermultiplets should give the vertex operator. So in a sense, we just accidentally found a nice way to generalize what they have shown already in 2008. So, but yeah. OK, so let me finish by remarking the relation to topological strings and matrix models. So there were, again, massive amount of literature on this relation of necklace of partition function Z to the partition function of the topological strings. But in the case, epsilon1 plus epsilon2 is 0, so which corresponds to the self-dual rotation or anti-self-dual rotation, depending on your convention. So in that case, it's known that necklace of partition function of the gauge theory is equal to the topological string partition function on a Calabi-Yau, which is given by changing this n fibranes into a fibration of n-1 ALE space. So this is my crude way of drawing ALE space. But you can use, for example, mirror symmetry to relate this to type 2A and type 2B side. And string coupling is epsilon1. And you can relate that to the theory of almost free chiral boson on the Riemann surface sigma, which is an n-sheeted cover. So you can relate that to n boson on the base. And it's also known that it's related to a matrix model. So in a sense, what we did is just to introduce another deformation parameter, epsilon1 plus epsilon2. So I think everyone could have guessed that the natural deformation of n chiral boson or n boson should be Toda theory. So we just made that generalization. And in that case, later Digraph and Waffer said that the matrix model side becomes modified by changing the exponent of the Van-der-Monde determinant. OK. So let me summarize. The idea was to wrap nm fibranes on a 4-manifold times Riemann surface. Then physical quantity on the 4-dimensional side becomes related to physical quantity on the 2-dimensional side. For example, I mainly talked about the relation between the necklace of partition function and conformal block on the 2-dimensional side. And under that mapping, the world volume fields phi 2 to phi n gets mapped to the expectation value of Tz to Wn. And many things to be understood, remains to be understood. For example, if you take the b goes to infinity limit, Liouville theory should become classical, right? So we should be able to see the classical Liouville boson with exponential interaction, but nobody has done that. So I hope somebody will clear that up. Thank you very much.
Questions?
You mentioned, in connection with the proof of this statement, you mentioned a nonlinear identity that's supposed to be satisfied by the partition function.
Oh, yeah.
Is there some physical understanding of why that identity is there?
At least I don't have any physical idea. It can be derived by choosing the internal line carefully so that it has a pole. So they just compare the poles of the both expression, and the pole itself is related to the same expression with lower degree of instantons.
It poles as a function of which variable?
Pole as a function of the primary, gauge theory vev A. Yeah.
If not, let's thank Yuji once again. Before I introduce the next speaker, does anyone in the audience have a computer remote?
I'll manage, don't worry.
So our next speaker is Jaume Gomez, who will tell us about the virtue of defects in gauge theories and 2D CFTs.
Okay, yeah. Okay, thank you very much. So let me start by also thanking the organizers for giving me the opportunity to speak. So essentially in this talk, what I want to do is to describe some recent connections between the beautiful and rich subject of two-dimensional conformal field theories and the physics of four-dimensional n equals 2 gauge theories that already has been advertised in the previous two talks. But in particular, what I'm going to do is to outline how you can use two-dimensional conformal field theory to calculate exactly certain interesting observables in four-dimensional n equals 2 gauge theories, in particular, computing correlation functions of non-local observables in four-dimensional gauge theories, exactly, using CFTs. Okay, so before I get into the core of the subject, let me give you some introduction and motivation for this work. So as we all know, solving exactly four-dimensional non-supersymmetric gauge theories is currently, and probably in the foreseeable future, completely out of reach. And it has been a very useful tool in the past to give more structure to four-dimensional field theories by making them supersymmetric, in a way that the constraints imposed by supersymmetry allows us to learn a lot of things about the dynamics of four-dimensional gauge theory simply because supersymmetry is much more constrained and allows us to solve the theory exactly for some observables. So here I listed a few examples of how supersymmetry has allowed us to get a lot of insights into non-perturbative effects, strong coupling dynamics, dualities, holography, and also interesting mathematical connections. A different line of development that has been happening in the last few years, both for non-supersymmetric but also for supersymmetric theories, has been the realization that non-local operators in field theory, that is, operators that are not defined at one space-time point but are defined on submanifolds in space-time, are ubiquitous in all gauge theories. And some of these operators are, of course, very well known and are textbook material, but some of the ones are less well understood and or have been constructed only very recently. So this is a list of the kind of the basic non-local operators that will be relevant for this talk. So we have operators that are defined on curves, which are the Wilson and the Tuve loops. Wilson loops, these are operators that you are all very familiar with. Tuve loops are kind of the magnetic analog of the Wilson loops. Then we can also have operators that are defined on surfaces as opposed to curves. And these are the surface operators that Davide talked about. And now you can also define domain walls, that is, objects that are defined in 3 dimensions that are codimension 1 from the point of view of the 4-dimensional gauge theories. So this is a very rich zoo of operators that exist in 4-dimensional gauge theories. And whenever the theory has duality, it's been realized that actually these operators are kind of very natural objects in which to study dualities on. And as we will see, they will play a role in our story. Okay, so the takeaway message of this talk is that the study of 2-dimensional conformal field theories, in particular TODA, Liouville and TODA conformal field theories, enriched by adding certain observables into these theories, allow you to compute exactly certain supersymmetric observables in 4-dimensional n equals 2 gauge theories. So this allows us to use all the powerful and beautiful tools of 2-dimensional conformal field theory to study interesting things in 4-dimensional gauge theories. So let me just give you an outline of what the basic dictionary, the current dictionary that we know between the 4-dimensional gauge theory and TODA conformal field theory. So the basic dictionary is the following. So the original work of Aldai, Gayot, and Tachikawa realized that the partition function of a 4-dimensional n equals 2 gauge theory is exactly captured by a conformal field theory correlator on a particular Riemann surface. On this talk, what I'll be mainly describing is how this dictionary, what is the conformal field theory dictionary to describe other interesting non-local operators in the gauge theory. And what we will see is that you can describe exactly the expectation value of Wilson and the 2 loops in 4-dimensional gauge theory in terms of a rich class of observables that exist in 2-dimensional conformal field theories that are also non-local from the point of view of the 2-dimensional worldsheet theory. So these are not the familiar primary local operators that we usually study in CFTs. These are operators that are defined on curves on the Riemann surface. Then you can have also surface operators that are computed by inserting a particular type of operator in the conformal field theory, which is called a degenerate operator. This will come back later in our study of loop and domain wall operators. And you can also find a dictionary between domain wall operators. These are the operators where you have the 4-dimensional field theory on the force sphere coupled to a 3-dimensional field theory on the S3 that lives at the equator of the force sphere. And depending on which type of domain wall you can have, there are several types of domain walls you can have. There is something called a Janus domain wall, where the coupling constant on the north hemisphere and the south hemisphere of the force sphere are different. You can have symmetry breaking domain walls. You can have duality walls. And all of them have a rather nice description in terms of objects in TODA conformal field theory. And I'll probably describe some of them during the talk. Okay, so let me give you a little bit of the background of our work. The basic background is the realization by Gayotto that you can associate a 4-dimensional n equals 2 gauge theory, which we will label by tau gn, to a Riemann surface with genus G and n punctures. And there is a set of rules of, given the Riemann surface, how to construct the 4-dimensional field theory. One interesting point of view in this picture is that this theory, there's a unique theory, but it admits many different Lagrangian descriptions. And the Lagrangian description of the theory is in one-to-one correspondence with the choice of a Pan's decomposition of a punctured Riemann surface. A Riemann surface can be constructed by gluing together pairs of Pans, or 3 puncture spheres, and tubes. And the different ways that you can sew the Riemann surface out of pairs of Pans give rise to different Lagrangian descriptions for the theory. So this is what I mean by this picture here. There is a unique Riemann surface and a corresponding unique theory, but this unique theory, depending on which corner of parameter space that you're studying, can have a different Lagrangian description. Okay? And essentially, the point is that you can construct this gauge theory from the basic building blocks of the Riemann surface, which is the pairs of Pans or trinions and the tubes that you use to sew the Riemann surface. Okay? And essentially, there is a dictionary that Gayot introduced of how, for each sewing of the Riemann surface, you can construct an explicit, well, in the best case scenario, Lagrangian description of the theory. Or sometimes a construction of a theory that doesn't have a Lagrangian, but where you can describe it in terms of some basic building blocks. So here I give an example of 2 different sewings of a genus 2 Riemann surface with 1 puncture. The showing is made manifest by showing where the tubes in the decomposition of the Riemann surface into trinions and tubes is. So here, for example, I have the tube going this way. Here I have the tube going that way. And to its kind of showing, you can associate a four-dimensional n equals 2 Lagrangian. And these two Lagrangians are supposed to be two different corners of describing the same unique theory tau to 1. Okay? So this is one of the key ingredients in our discussion, the fact that we can associate a four-dimensional gauge theory to a punctured Riemann surface. The other very important piece of information that was key, not only for me, but also for the work of AGT, is the beautiful computation that Peston made of the partition function of four-dimensional n equals 2 gauge theories on a force sphere. So he was able to use powerful techniques of localization to do an exact computation of the path integral of the theory on this round force sphere. Okay? And the basic structure that we will need for this talk is that this partition function essentially takes the form of an integral over some parameter that has interpretation as the vacuum expectation value of a scalar in the four-dimensional equals to vector multiplet of the theory of the modulus square of this Nekrasov partition function that we have been hearing about in the last two talks. Okay? And as already has been said, this Nekrasov partition function is a particular deformation of the instanton partition function on the force sphere. But I should mention that this is really the partition function of the physical theory on S4. There is no, this is really the physical partition function on the force sphere. Okay? And the thing I want to notice is that one nice observation by looking at this formula is that the partition function takes a form that looks holomorphically factorized, because here I have a bar. And in fact, the contribution of the instanton partition function, remember that we're doing the partition function of the theory on the force sphere. This contribution comes from the north pole of the force sphere. This contribution comes from the south pole of the sphere. And it has this holomorphically factorized form. Okay? Now, the other thing that this resembles is the fact that also there are other objects that we've seen before that also have a holomorphically factorized expression, which is the correlation function of local operators in two-dimensional conformal field theory, where essentially you can compute the correlation. We know that we can compute the correlation function of any punctured, on any punctured Riemann surface by essentially showing the Riemann surface in different ways. Okay? And essentially, what this formula tells us is that the correlation function can be always reduced to the following form. By introducing a complete set of states into the correlation function, you can reduce the computation of any correlation function to the product of three-point functions of primaries. These are associated to the trinions, or the pair of pans in the decomposition for each of the primaries. And there is one associated to each vertex, which corresponds to a pair of pans. And then there is a sum. When you have a complete set of states, the sum decomposes into a sum over the primaries of the CFT and also over all the Virasoro or W descendants of the CFT. And the information about the descendants is completely, you could say, kinematical, in the sense that this is a property that does not depend on the CFT that you're looking at. It's a property of the Virasoro or the W algebra. Okay? So this is why the conformal field theory correlator takes this elegant expression, where you essentially reduce any correlator to a product of three-point functions and these conformal blocks that know about the descendants. This is true in any dimension. What's special about in two dimensions is that the conformal blocks are factorized into a contribution from the left movers and a contribution from the right movers. Okay? The realization that was made by Aldai, Gayotto, and Tachikawa was that the partition function that Gayotto wrote down on the four-dimensional equals 2 gauge theory on the force sphere is exactly captured by a particular two-dimensional Toda correlation function on the corresponding Riemann surface, okay? Where there is a certain dictionary of how the parameters, the mass parameters of the Lagrangian of the four-dimensional equals gauge theory get mapped into for example, the quantum numbers or the moment or the total momenta of the vertex operators that enter in this particular correlator. Okay? One immediate consequence of this observation is that since here, even though the correlation function I wrote here is been written for a particular choice of Pan's decomposition sigma, one of the basic properties of CFTs is that the operator product expansion is associative. So the correlator should not depend on your choice of Panzi composition, which maps via this dictionary to the statement that that's a statement of modular invariance of correlators in two-dimensional CFT. And this implies modular invariance of two-dimensional CFT gets mapped to the S-duality of the four-dimensional gauge theory. So from this, by this connection and using this observation about modularity of CFTs, you find that the Pestum partition function on the fourth sphere is invariant under S-duality. Okay. So in the rest of the talk, I will sketch how to use two-dimensional CFT to compute exactly loop operators and domain wall operators in four-dimensional gauge theory. And this is work based with Drucker, Kyoto, Okuda, and Teschner into separate papers. Okay. So the basic character that's going to allow us to do these computations of loop and domain wall operators in four-dimensional gauge theory will be a particular non-local operator that exists in all two-dimensional conformal field theories, which are known as topological defect operators. Okay. So let me first, before discussing how you do that for Liouville and Toda, let me just tell you a little bit of the background, what these operators are and how are they defined. So any two-dimensional conformal field theory can be enriched by inserting a defect loop operator. This is an operator that's supported on a particular curve on your Riemann surface. So here I drew a particular curve on the Riemann surface. Okay? It turns out that you can define an operator on the Riemann surface which is defined by saying that this operator commutes with the stress tensor of the conformal field theory. That is the statement that the operator is invariant under the two copies of the Virasoro algebra, or W algebra if you're doing Toda, of the CFT. Okay? The fact that this operator, which is defined on the curve, commutes with a stress tensor tells you that, and the stress tensor generates conformal transformations, is a statement that this operator, since conformal transformations are allowed to change the shape of the curve, it's a statement that these operators only depend on the homotopy class of the curve, because a conformal transformation can move the curve around, but the operator should be invariant under it. And also, since it commutes with the stress tensor, these operators are labeled by a curve, but also by a choice of representation of your chiral algebra. Just to give you some intuition of what these operators are, at least semi-classically, you can think of them as Wilson loops operators in the two-dimensional conformal field theory, where you write the usual expression for a Wilson loop, where L is a particular flat connection, which mimics the fact that this particular observable does not depend on the precise choice of the curve, only the homotopy class of the curve. For the case of Liouville and Toda, this L should be thought of as the lax connection whose zero curvature condition reproduces for you the classical equations of motion of Liouville and Toda. So clearly, this operator is intimately connected to the integrability structure of two-dimensional conformal field theories. Okay? One immediate observation from that Petkova and Joubert did, I mean, these operators were first defined by Petkova and Joubert 10 years ago in CFTs, in rational CFTs. Since this operator commutes with two copies of the Virasoro algebra, it means that this operator acts on the identity for any subspace in the space of Hilbert states in a particular representation. So it's a diagonal operator for each representation in the Hilbert space of the theory, modulo some coefficients that one has to determine, d mu alpha. Okay. Another way of thinking about these topological defects is you have a Riemann surface that separates, sorry, you have a curve that separates the Riemann surface into two pieces, and this loop operator can be thought of as a boundary state by using the folding trick. So you can take the tube, you can fold it into two, and then the operator, the topological defect operator, gets mapped to the boundary conformal field theory for the product of CFT, of the first CFT with the parity conjugate of the second one. Okay? And it's called a permutation boundary state because instead of what you're doing is gluing the holomorphic stress tensor of one theory with the anti-holomorphic stress tensor of the other one. Okay? So just like boundary states, the insertion of these objects into correlators imposes consistency conditions. And essentially by demanding that the operator the insertion of a topological defect into the torus partition function has a Hilbert space interpretation, which is essentially the analog of the Cardi condition, you essentially can derive what the coefficients of the determine the operator are. And these are given by this ratio, what are called the modular matrices of the CFT, which essentially relate the characters of the various representations of your CFT on the torus, how they transform under a modular transformation. So this very simple expression of these loop operators is valid whenever the curve that the operator is defined on wraps a tube in the Pansy composition of the Riemann surface. Because then this operator is in some sense just measuring the quantum number that's propagating across the tube. But we will be interested in more general situations where the curve, and I draw it here an example, where the curve that the operator is defined on does not encircle a tube in the Pansy composition. In particular here, this guy does not wrap the curve that will give you the Pansy composition, which will be here. Okay? So in general, the expression for the topological defect will be more complicated. And a useful way of phrasing these topological defect operators is by the way they act on the conformal blocks of the theory. Okay? And something that you can say very generally, just from the fact that the operator commutes with the two copies of the stress tensor, is that a topological defect, a correlation function in the presence of a topological defect, still has a holomorphically factorized form. And in general, it will act non-diagonally in this particular way. Okay? And this mu is essentially the matrix element of your particular topological defect when you insert into the correlation function. Okay? So I think that it's nice that is that even though it's not apparent from the definition of the topological defect operator that I gave, it turns out that this definition is completely equivalent to an older definition of loop operators that were used very heavily in the 80s in the context of rational CFTs, which are the Berlinde loop operators. And gives you kind of a very efficient tool in which to compute some quantities by mapping Berlinde loop operators into these topological defects. Okay? The fact that they are really related to topological defects, combined with what I already said, that semi-classically, these operators are measuring semi-classical monodromies of field configurations. Physically, what these operators are doing is measuring monodromies induced by particular chiral operators. These are operators that are only either holomorphic or anti-holomorphic, acting on the conformal blocks. Okay? So now we're going to study these particular operators in Liouville theory. And I already said that these operators, since they commute with the stress tensor, have to be classified by a representation of the Virasoro algebra. So what you want to do is essentially study the different representations of your particular chiral algebra, which for Liouville is the Virasoro algebra. And so Liouville, representation of Liouville are labeled by the momentum, what's called the Liouville momentum. And which take this particular, the primaries are created by vertex operators of this particular form, and this is their conformal dimension. In Liouville theory, there are essentially two different representations that you can have, which are called degenerate and non-degenerate representations. And the first one, it's in analogy with the construction of boundary states in Liouville theory, we will call ZZ, by homologic of topological defects, are labeled by a particular degenerate representation, which is when the momentum of the primary takes this very particular form where R and S are integers. In order to compute the expression for the topological defect, what we have to do is compute the ratio of modular matrices for this particular representation, which in this case is very simple because the character of the degenerate representation is particularly simple. It has, this essentially is the dimension of the primary, and one of the important properties of the degenerate representation is that it has a null state in the descendants, and that's what this minus does. Essentially, it removes the Berma module associated to the null states. And then just by doing a simple Fourier transform of the character, you can compute the modular matrices, and therefore the expression for the topological defect operator of the ZZ topological defect operator, okay? Which is just a simple ratio of sign functions. Likewise, we can do the same thing for the other type of representation that we have in Virasoro, which are the non-degenerate representations. These are the ones that have no null states in them and have a very simple character. And again, you can compute the expression for the topological defect just by doing a Fourier transform of the character expression. As I said before, these very simple formulas in terms of the ratio of the modular matrices are valid whenever the topological defect is wrapping a tube in a particular choice of Pan decomposition, so that the operator really acts diagonally on the conformal blocks. In general, it will not act diagonally. So here I give an example of, say, in the 4-puncture sphere. This will be the right insertion that you would have to put into the correlation function if the topological defect was wrapping this particular circle that separates, which is essentially wrapping the tube that defines this particular Pan decomposition of the Riemann surface into a trinium here, and a tube connecting them. Okay? So now what I want to do is to use topological defects to compute certain gauge theory observables. So the first thing that we have to do is identify, if anything, whether there are candidates in the 4-dimensional gauge theory that compute these particular interesting observables in 2-dimensional CFTs. So let's start first with the interpretation of the homologic of topological defects. Okay. As I already said, in the choice, in the frame or the choice of Pan decomposition where the operator is wrapping a tube, the correlation function in the presence of a Liouville of one of these topological defect operators takes a very simple form. The conformal blocks are eigenvectors of this loop operator, and all that you have is essentially to insert the ratio of modular matrices that are already computed for you. So the expectation value of topological defect in the presence of n primary operators in Liouville takes this very particular form. Okay? Now, in the study of the connection between Liouville and 4-dimensional gauge theories, we should look at Liouville at the value of central charge 25, which corresponds to this parameter b equals 1, which is related to the background charge of the scalar field in Liouville theory. For this particular value of b, of the background charge, a basis of defects is given by this particular choice of operators, where you have one, and the other one is an arbitrary integer. Okay. For this particular choice of integers, what you find is that this expression reduces to this ratio of signs, but this is nothing but the trace of this particular holonomy in the spin Z representation of SU2. Okay? So what you found is that the insertion of ZZ topological defect inserts kind of a holonomy for an SU2 connection in the spin Z representation. Okay? And now by using the connection that was already known before between conformal blocks in Liouville and the Nekrasov partition function, what you find is that the expectation value of this topological defect exactly computes for you the expectation value of a Wilson loop in 4-dimensional gauge theory, because this guy is exactly the expression for the Wilson loop. And this exactly reproduces a further generalization that Peston had of the exact computation of an expectation value of a Wilson loop in 4-dimensional and equals to gauge theory. Okay? So we found that ZZ topological defects compute when they wrap a circle in the Pan decomposition, they compute Wilson loop operators. And we reproduce, doing this way, answers that were known before. But now we want to do better and try to use this Liouville connection to compute things that we didn't know before. And in particular, one of the basic questions you can try to ask is, what is the 2-dimensional CFT description of two loop operators in the 4-dimensional gauge theory? These are operators that instead of inserting an electric source, they insert a magnetic source. Okay? An important observation that was made by these authors is the statement that the electric and magnetic charges of loop operators in the gauge theory are encoded in the choice of curve on the Riemann surface. So once you have a Pan decomposition, remember that I said before that the choice of Pan decomposition corresponds in the gauge theory to a choice of duality frame, or one of these corners in the cusps of the web diagram. And once you choose a Pan decomposition, whether something is electric or not, a particular operator is electric or not, depends on whether this curve wraps one of the tubes in the Pan decomposition or goes across it. Okay? So in particular, in this choice of the Pan decomposition that we had before for the 4-puncture sphere, a magnetic operator would be one that kind of traverses the tube. So the tube in the Pan decomposition would be going like this. Notice that this curve crosses the tube in the Pan decomposition. And these are the operators that you want to associate with tooth loops, or operators that carry magnetic charge. Okay? So essentially what we have to do, remember that I said that the topological defect, more abstractly, what it does is compute the monodromy action of a chiral operator in the CFT acting on the conformal blocks. Okay? So what we have to do is compute the monodromy induced by a chiral operator in the CFT, which carries the quantum number of the corresponding topological defect, acting on the conformal blocks. Okay? Luckily, there is a very beautiful and powerful technology to compute this, because monodromies of conformal blocks can be computed by just concatenating basic generators of monodromies that relate essentially the analytic continuation of conformal blocks in different channels. Okay? So it's known from the 80s that any monodromy can be computed by concatenating essentially these basic generators of monodromies, which relate conformal blocks in different channels. And these are known as the fusion and breading and the S moves. For this talk, we will only worry about the fusion and the breading move. Essentially, what this does is relate the analytic continuation of the conformal block associated to the 4-puncture sphere on the S channel to the conformal block associated to the T channel by this matrix, which is called the fusion matrix. And there's also an analog operation that you can use to compute sequentially the monodromies, which is called the breading move, which essentially exchanges two consecutive lines or two consecutive operators in your conformal block. Okay? So essentially, by following the path of your primary along your Riemann surface, you can compute the monodromy by just putting together the associated fusion and breading matrices in the CFTs. So you'll have a sequence of moves. For each move, it will be either one of these three generators, and the total monodromy is just the product of the various matrices. So let me give you an example in pictures. I will not write any formulas because they get a bit complicated, but I just want to give you a flavor pictorially of the kind of things that you have to do. So we want to compute the simplest tooth loop in the simplest possible theory, which is one of the simplest, which is n equals 2 gauge theory with a gauge group SU2 and with 4 fundamental hypermultiplets. Okay? I already said that what a tooth loop does is compute the monodromy acting on the conformal block when it goes around the magnetic cycle in this Pan decomposition. So essentially what I have to do is create the particular field that labels the topological defect and compute the monodromy that is acquired by moving this particular primary field across this particular closed curve. Okay? In the picture of conformal blocks, you can associate to each choice of Pan decomposition a particular conformal block. And essentially what I'm doing now in this picture of conformal blocks is moving this particular degenerate field that it may not be degenerate, but in this particular case it is degenerate, around the image on the trivalent graph of the curve that is being traversed on the Riemann surface. So essentially, let's follow a little bit what's happening to this guy. So what I'm doing is first doing a fusion move that relates this channel to this channel, and then I do essentially 3 braiding moves that moves this line twice here. Then I braid back again, and then I refuse back. If you follow carefully the diagram, this is exactly doing this picture. Just moving this particular operator across the whole entire Riemann surface. And the claim is that the expectation value of the tooth loop is obtained by the total monodromy acquired by following all these steps. Okay? You can do an analogous thing for another simple case, which is the n equals 2 star. This is the mass deformation of n equals 4 super Young mills. In this case, the Riemann surface associated to this particular theory is the once puncture torus. And if you want to compute a magnetic operator, a tooth loop, you have to compute the monodromy associated to the A cycle on the one puncture torus. And in terms of the corresponding conformal block, you're computing this sequence of moves. So you have to do fusion, fusion, and then fusion back. Okay? So this gives you a very effective rule of computing the expectation value of two loops. So just to tell you a particular completely explicit formula that you can obtain when doing these procedures, this is the prediction out of this computation of the exact expectation value of a tooth loop in this particular theory. And notice that it kind of has a simple form. And unlike the case of the Wilson loop, the main difference with the case of the Wilson loop is that notice that the momentum that labels the holomorphic and anti-holomorphic conformal block has been shifted. And that's due to the fact that when you move a field across the Riemann surface, it has a non-trivial fusion with the quantum numbers associated to the tubes. And that essentially is responsible for the shifting of these quantum numbers. So the thing that you can show is that actually this answer is consistent with the expected action of S-duality on Wilson and the tooth loops. Okay? So what we find is that the ZZ topological defects in Liouville theory compute exactly the supersymmetric loop operators in four-dimensional gauge theory. So in the last few minutes, what I want to show is answer the question of what is the gauge theory interpretation of the other topological defects. But in order to answer that, it is useful to gather more data, and instead of looking at topological defects in Liouville, to look at them in TODA CFT. So let me just go quickly through that because this has been already mentioned. What I want to do is construct topological defects in TODA. And again, these are labeled by representations of the W symmetry, which you can construct by looking at the CAC table, a CAC determinant for the representations constructed using these higher spin currents. Okay? An answer that I can already tell you is that there are two types of representations also here. If you look at the degenerate representations of TODA, what you find is that when the value of the central charge is corresponding to B equals 1, where you have a gauge theory interpretation, what you find is that the degenerate topological defects, which are in fact labeled by a representation R of the Lie algebra, because a TODA CFT is labeled by a Lie algebra, what you find is that this object exactly inserts not only in the case of before, we had a Wilson loop in an SU2 gauge theory. What you find in the general case of TODA is that this particular topological defect inserts a Wilson loop in a representation R of the Lie algebra G. So this extends the dictionary by saying that degenerate topological defects in TODA correspond to Wilson loops in the four-dimensional gauge theory. Then there are more exotic representations that you can construct in TODA, which are called semi-degenerate. And they carry two basic labels. One is purely imaginary TODA momentum, and then a representation R, little r, not of the original Lie algebra, but of some subalgebra H in G. Okay? So now what you have to do, and that's kind of one of the technical things that we did in this last paper, you have to compute essentially the characters associated to both the non-degenerate and the semi-degenerate representations, compute the modular matrices, and that gives you an explicit expression for the effect that they have on the correlation functions in TODA. And this is what you find. Let me just point out a couple of things. Since, again, I'm looking at topological defects that wrap a tube, the conformal blocks have unshifted momentum. What you have here is a ratio of signs, where A is the Liouville momentum. You have a Wilson loop, exactly the expression of a Wilson loop for the gauge group, for this subgroup H, and then you have this particular phase. And essentially what we did is to construct a domain wall in four-dimensional N equals 2 gauge theories that by analyzing the four-dimensional partition function using extending Peston's localization techniques to the inclusion of these operators, exactly reproduced this expression. So essentially what we did is to define, which is already known in the case of N equals 4, to define symmetry breaking domain walls. So these are walls that are going to be localized on the three-sphere, on the equatorial S3 of the four-sphere. And these domain walls are defined, which preserve half of the supersymmetry. And the boundary conditions that you have to impose on the domain wall is to take the fields in the three-dimensional N equals 2 vector multiplet that you get by decomposing the four-dimensional N equals 2 theory into three-dimensional N equals 2 multiplets. You have to take the fields that take values in G minus H to vanish. This is a supersymmetric domain wall configuration. And then what we can do just by looking at this formula is identify what the various terms are coming from. So this trace of R has an obvious interpretation to the fact that this domain wall can be enriched without breaking any further supersymmetry with a Wilson loop. But now the Wilson loop only knows about the unbroken gauge symmetry of the domain wall, which is H. So you have a domain wall that breaks at the domain wall G to H. You can add supersymmetrically a Wilson loop for the H gauge group. These M parameters, which in total corresponding to momentum, correspond to Fayet-Leopolds parameters that can live in this domain wall. Essentially, what you have to do is to write down supersymmetric coupling on the domain wall. And this term can be interpreted as the coupling of Fayet-Leopolds parameters to the unbroken U1s that are localized at the domain wall. And the other thing I want to mention is that this interpretation of this ratio of signs is precisely that it removes so the first thing I want to say is that this sign square is exactly the one loop determinant contribution of a three-dimensional n equals 2 vector multiplet. And the fact that you get this ratio of G over H is essentially the statement that you're removing the contribution from precisely the fields that you set to 0. Okay? So by analyzing more carefully than I did here the four-dimensional path integral for this domain wall, what you find is you exactly reproduce this expression. So we find that the semi-degenerate defect operators correspond to symmetry-breaking domain walls. Let me just very quickly do one more example, and then I'll essentially stop, of another kind of interesting correspondence that you can find between objects in two-dimensional CFT and objects in the four-dimensional gauge theory, which is the following. In four-dimensional gauge theories, it's been known for a while that you can construct what are known as Janus domain walls, these are four-dimensional field theories where the coupling constant can jump discontinuously across a domain wall, say the equatorial three-sphere or the four-sphere, so that you have two different gauge couplings on the northern hemisphere and the southern hemisphere of the four-sphere. The statement is that if you want to study the partition function of the Janus domain wall on a four-dimensional equals to gauge theory, that this corresponds to inserting a generalized defect operator on the Riemann surface into the CFTs. And what I mean by a generalized defect operator is that instead of gluing across the interface the stress tensor of the two theories, is what you do is you do a conformal transformation and then you glue. Okay? If you do that and you take F bar to be not the complex conjugate of F, essentially, what happens is that you're changing the complex structure on the holomorphic and anti-holomorphic blocks so that the right movers and the left movers of the CFT are actually living on two different Riemann surfaces. They have different moduli, essentially. So in particular, if you take the generalized defect operator associated to the trivial representation, even that gives you something interesting. It tells you that the expectation value of such an operator is the product of two conformal blocks, but evaluated at different values of the moduli of the Riemann surface. And again, by extending Pestun's computation of localization in the presence of a Janus domain wall, this is exactly the answer that you get from independent gauge theory analysis. So we find that these generalized defect operators correspond to Janus domain walls. We also have a dictionary for what are called duality walls, but I don't have time to discuss them. So let me conclude. One of the messages I wanted to say is that there is an interesting class of loop operators in two-dimensional conformal field theories that have lots of interesting properties. I want to reiterate that non-rational two-dimensional CFTs of the Toda type capture exact quantities in four-dimensional gauge theories. In particular, they capture the dynamics of Wilson and Tooth loops and domain wall operators. It is the hope that these non-local operators in four-dimensional gauge theories will be able to provide us insights into gauge theory dualities because they play a very important role. They participate very actively in dualities. And essentially, Toda CFT, which is still not completely solved, what it's doing is actually providing us a window into non-Lagrangian four-dimensional gauge theories, because I didn't emphasize it too much, but many of these four-dimensional gauge theories for the higher rank do not have explicit Lagrangian descriptions. And these computations into the CFT, in a way, are giving you information about these non-Lagrangian field theories. So it is the hope that maybe by studying this further, we will learn something interesting about the kind of the role of non-Lagrangian field theories in four-dimensional physics. So with that, I'll stop. Thank you.
We have time for one or two questions.
What are the M-theory interpretation of those defect operators?
Well, so it depends. So
Yeah, for the degenerate ones.
yeah, so there's an M5 branch.
Yeah.
So for the non-degenerate, there's an M5 branch. You can have M5 branch that wrap a curve on the Riemann surface and give you a domain wall on the four-dimensional theory.
If not, let's thank Jaume again and break for lunch.